My name is Zhenxiao, and I'm from UC Riverside. In this talk, I'll present our work SymFit on binary code Concolic execution. So in this work, our goal is to improve the efficiency of existing binary code Concolic execution. And we focused on the binary-only situation as mentioned in the previous talks. The binary-only situation is a very common case in software testing, such as analyzing the proprietary software and dependencies, stripped binaries, or firmware where only the binary blob or binary code is available. And we focused on the improving the efficiency as we found in our evaluations. So the existing solutions suffer from heavy instrumentation overhead, slow shadow memory access, and also inefficient symbolic state management. So let's look at the evolution of binary code Concolic executors. First, we have tools like Anger and S2E. So typically, it starts by executing the binary concretely and switch to certain part of the code or functions. And this process is usually predefined, which requires manual efforts, engineering efforts to identify the function of interest or code of interest. And it can potentially overlook symbolic instructions that propagate from the input. And more importantly, this two-stage happens in different execution space, meaning that context switches are needed, and it takes non-trivial overhead to synchronize the state between the concrete and symbolic environment. There's another lines of work, like QSym and SymQEMU, that tries to fix this problem by directly instrumenting the symbolic emulation logic into the target binary at runtime. So essentially, this symbolic emulation logic runs together with the target binary to avoid the context switches and the heavyweight state synchronization. However, there are still overhead in terms of the concreteness checking and the symbolic state management. And in the following slides, I will focus on these two aspects. So this is typically how the instrumentation-based approach works. For every instruction, it instruments a helper function that essentially handles the symbolic effects of this instruction. However, not every instruction is symbolic. So inside those helper functions, you will see some code like the conditional checks like this to check whether both operands of the instructions are concrete. If so, it will just return instead of calling the function to emulate the symbolic behavior. Same thing for shadow memory access. It will first read the shadow memory, read every byte of it, and to see whether the target symbolic memory is actually symbolic or concrete. So such strategy is fine-grained in terms of checking symbolic instructions and avoid unnecessary emulation. But it's very inefficient because it has to pace an overhead of function call and also accessing the shadow variable and the shadow memory. As you can see from our evaluation results, so SymQEMU can have an average of 34 times slowdown compared to the vanilla QEMU, and this is in the setting where all the inputs are concrete. So to improve this instruction level checking for variables and shadow memories, we utilize a fine-grained but efficient approach. The idea is that we check at basic block level, and for every basic block, if all the CPU registers are clean, which means all the instructions in this basic block can only deal with concrete variables. The only exceptions is load and store. So load and store can potentially read and write from to the shadow memory. So for such basic blocks, we can execute them. We don't need to instrument every instruction, and we can execute them with very lightweight instrumentation for load and store. On the other hand, when not all the CPU registers are clean, we'll just execute this basic block with full instrumentation to make sure the symbolic variables are propagated correctly. Also, we show that over 80% or 90% blocks are executed concretely, so which means this kind of optimization can greatly boost the performance. As for the shadow memory checking, in the existing works like QCM and SymQEMU, it used a two-level map to model the symbolic memory. So when checking the symbolic memory, it first locates use the page start to locate in the map to locate the shadow memory modeling and read every byte of it to figure out whether this address is clean or not. Inspired by the TLB design in QEMU, we use block level checking, which means we buffer the recently accessed clean blocks. And for every shadow memory access, we first check whether there is a cache hit in this buffer. And if so, we know that this shadow memory will be clean, and we can directly return. So this approach capitalized on the locality of the shadow memory access, and also it depends on the size of the design of the block. In the original design of TLB, the block size is 1 page, but this is apparently not a good choice for us because even a single symbolic byte will mark the whole page as symbolic. So we experimented different levels of the block from 32 bytes to 2048 bytes. And we simply choose the best player, which is a block size of 512. And you can see that it can have cache hit rate over around 95%. And what this cache hit rate will not be like a typical TLB hit rate, which is around 99% of hit, because when we calculate the hit rate, every symbolic access will eventually be a miss. So, the cache rate will not as high as what we can see in the TLB. As for symbolic state management, we borrowed the idea from another research work called SymSan. SymSan works for source code, is a source code-based concolic execution. We spent some engineering efforts to make it work in our binary code concolic execution tool. So, but essentially the idea is the same. In the backend of QCM and SymQEMU, it maintains the symbolic expression in a tree data structure. So every symbolic expression is essentially a pointer, and the allocation of the expression is a malloc on the heap. Instead, we maintain the symbolic expressions in a union table. It's an array, and every symbolic expression is identified by a 32-bit integer, which is the label, and is also the offset of that specific symbolic expression in this array. So with this design, the allocation becomes a simple atomic increment of the last allocation label. And we can achieve very fast lookup of the symbolic expression and also the allocation. For the shadow memory, instead of modeling them in a two-level map data structure, we use direct mapping between the application memory and the shadow memory. So essentially, we trade off the space complexity for time efficiency. So to put everything together, I want to present SymFit as an efficient symbolic tracer, which means we decouple the symbolic tracing functionality and the constraint solving part. And this is because we found that the constraint solving is a blocking task in concolic execution, and a lot of the time, the engine is just waiting for the result returned back from the constraint solving. Once we decouple them, this constraint solving part can be paralleled because most likely they're independent and they don't have much right contentions. And more importantly, we want to mention that constraint solving is only one application using symbolic expressions, there are a lot of other downstream tasks that we can do once we decouple this two-step. So here's the overflow of SymFit. We build our tool on top of QEMU. We instrument the logic dynamically using the QEMU dynamic binary translation step. The instrumentation will alter the execution of the target binary, switch between the concrete mode and the symbolic mode. In the symbolic mode, we will maintain and store the symbolic expressions in this union table for fast lookup and allocation. For shadow memory, we first try to hit the fast pass, which is this cache lookup. We only fall into this slow pass of shadow memory access when there's a cache miss. And accessing this shadow memory is actually efficient because we use the direct mapping of the memory. So our symbolic tracer will produce symbolic constraints that supports downstream tasks like path exploration in the hybrid fuzzing situation, and also crash analysis and deduplication. So some evaluation highlights. We compared with SymQEMU on the fast-bench programs. We show that when all the inputs are concrete, we can achieve as fast as 10 times speed up than SymQEMU. And with the inputs are symbolic, but with disable solving, we can still have an 8-time speed up. And even when solving is enabled, which is the dominant overhead, we can still achieve a 5 times speed up. And some evaluation results regarding the hybrid fuzzing, we simply pair our Concolic executor with a fuzzing instance and compare the coverage growth. Well, we can see from the results that for some of the programs, we can achieve faster coverage growth, but for the rest of them, it's pretty much the similar result. And we believe this is because in this combination of fuzzing and the Concolic executor, fuzzing is still the driving force in the path exploration, and potentially a smarter combination of hybrid fuzzing is needed. Also, I want to show a unique application of using the symbolic constraints for crash deduplication. We use the Magma benchmarks to collect the. So we ran our tool on the Magma benchmarks, and we collect the symbolic constraints from the last branch before the crashing site. We also collect constraints that has input dependency with the last branch. For the deduplication, we simply group all the seeds that produce the same or similar symbolic constraints. And we can show that this approach is, well, while it's not perfect, it can achieve 80% F1 scores, and more importantly, it's very efficient. So that's all about SymFit, and open source, you can find the code in the GitHub repository. I mean, the process of updating our tool to the latest QEMU, I also built a kernel version of the SymFit that can trace how the symbolic value propagates in the kernel functions. If you are interested, you can check it out and also check out our paper. And I'm also actively looking for jobs. So if you think there's a good fit, please feel free to reach out. With that, I can take any questions from here.